Hi, I'm Professor Noeln Scaife, and I'm going to be talking to you about the big idea of data security. Now, there's a lot to cover in this idea, so much so that we won't have time to cover all of the nuances and tools. However, I hope I can give you a broad overview of the main topics. Now, data is ubiquitous today, and it's not only the data that you create, like your photos. For example, your cell phone provider can and likely does store the location of your phone at all times. The amount of energy you use at home can tell your power company if you're home, and app developers know how much time you spend in their apps and what you click on. Now, this data has value, and in many cases, it's the only irreplaceable aspect of a computer. It's worth taking some time to think about this. If your computer stopped working today, you could likely repair or replace it. But if your photos were deleted, would you be able to get them back? Many people would not. So we want to provide some security for this data. In this domain, we typically define this in terms of confidentiality, integrity, and availability. For each of these, we could also provide some context about the data, specifically whether it's at rest, meaning that it's in storage somewhere waiting to be used, or in motion, meaning that it's in the process of being moved between two things. Now, when we talk about confidentiality, we're talking about preventing some unauthorized party from viewing some data. And the first thing we want is access control. And so the property of least privilege is critical here, that people should have the least amount of access that they need to perform a task. Now, in an ideal world, we might be able to define all of the people that could access something, then grant access to what they need. But in practice, this is a monumental task. And it implies, too, that no one will try to subvert our system. So the tool that we typically use for managing confidentiality is encryption. Now, encryption comes in two general categories, symmetric and asymmetric. And both of these are useful for different things. Think about the key to your home. Is everyone's key the same? This is the idea behind symmetric encryption. The same key can both encrypt and decrypt some data. This process is very fast, and we use this when we need speed. But using our home example, however, let's assume you come home, something is missing, and no one appears to have broken in. So who took it? Since everyone uses the same key, it's hard to say. And since anyone that you gave a copy of the key to could have themselves copied it and given it to somebody else, there's no way to know how many keys exist or who has them. And so the problem here lies not in that the encryption itself is bad or broken, but that managing keys is hard. So now I want to talk about asymmetric encryption. So what if instead of two parties sharing a key, we could break that key into two pieces? One of the pieces I'll keep, and I'll call it a private key, and I won't give this out to anyone. The other, we'll call it the public key. I'll give that one to everyone. I'll even put it on my website. It turns out we can do some really interesting things with this. If you want to send me something privately, you could look up my public key and use that to encrypt the data. Since only I have my private key, remember I don't give this out, only I can decrypt it. If someone else sends me a message, they would follow the same procedure. And both of these types of encryption grant us the ability to make data confidential. But like I said earlier, managing keys is often the hardest part of successfully implementing encryption. For example, what do I do with my private key? How do I protect that? We could talk for hours about the trade-offs and ways to protect encryption keys, but the takeaway that I want you to have from this is simply saying something is encrypted is a gross oversimplification. So let's talk about integrity next. And what we mean by integrity is that the data is verifiably unaltered. Consider bank transfer. You want to transfer $50 to a friend, but after you submit that request, an attacker changes it. So now your $50 transfer is for $5,000, and instead of your friend, it's now going to the attacker. How could the bank know the difference? There are many tools for verifying the integrity of something. We're only going to talk about digital signatures. So let's go back for a second to asymmetric encryption. Do you remember if you encrypt something with my public key, only I can decrypt it using my private key? But what if we reverse this? If I encrypt something with my private key, anyone could decrypt it with the public key. Now, the data isn't confidential since anyone can decrypt it. It does tell you, though, that only I could have created this signature and that the data is unaltered. And so many of the cryptographic tools we use for confidentiality can also provide integrity. It's not just important for banking, though. We use techniques like this to make sure, for example, that software updates haven't been tampered with and that digital contracts haven't been altered. So let's talk about availability next. Availability means that the data is completely accessible. You may have heard of denial of service attacks, and these types of attacks try to impact the availability of systems and data. The idea, of course, being that if a business's customers can't access the data, there might be some financial harm. And this isn't strictly related to systems, though. Consider our banking example. If instead of altering the message from $50 to $5,000, they simply prevented the request from being delivered. And this might actually seem harmless for you and me, but this could cause quite a bit of chaos for a large business or government. If, for example, a military installation sent a message every day that says, "We're here and we're okay," and one day that message never arrived, it's not hard to see how this might cause a problem. Every system has to handle availability a little differently. When we build systems, the best practice is to consider what would happen if any piece of it is offline or experiences delays. With data, for example, we might consider having multiple copies in different locations. Or we could use other methods to make data recoverable if some of the bytes are missing. Ultimately, all of these come down to risk and risk acceptance. And as you'll see in the Risk Big Idea video, securing systems and data is ultimately about making trade-offs. For availability, for example, storing 2 copies of every file means that your storage costs are doubled. You also have to move that data around to make the copies, so your bandwidth costs might be increased. On the other hand, maybe that data is not important enough that the cost of losing it is less than these storage and network costs. These are real decisions that are made every day by businesses around the world. And finally, I want to talk briefly about privacy. So we live in a world where more data is created and stored about us every day. And many people feel they don't have anything to hide, so privacy is not important. However, I suspect none of these people would allow strangers into their homes to sift through their belongings. So why is it important? Simply put, it's none of anyone else's business what you or I do in our homes or with our devices. There are many things that can go wrong when privacy is lost. Old data about you can be viewed out of context, and that can lead to false assumptions about your behavior or your beliefs. Having privacy limits the amount of information about you, which has limitless possibilities for advertisers, governments, and other types of organizations. This is, of course, why data about us is so valuable. And so I hope I've convinced you that data security is important and it's difficult, and that the only way we can get better at managing our data is by understanding its value and how to appropriately apply controls to limit unintended consequences. Thanks.